chapter, we're going to start looking at applications of derivatives. In this lesson, we're going to continue our look at related rates. All right, everyone, let's do some more related rates. Okay, so here we go. A bubble is inflated at a rate of 2 centimeters cubed per second. Okay, so again, right off the bat, I know, okay, a rate of change. I know dV by dt is going to be 2 centimeters cubed per second. Okay, and I know that it's positive because it's being inflated. Okay, we're adding the air to it. How fast is its surface area changing? Okay, so we are looking for dA by dt. Okay, I know that's what I'm looking for. When its radius is 12 centimeters. Okay, we're looking for it at the specific moment that r is equal to 12. Okay, now I've got V and I've got A, except that I don't actually have a formula for volume, okay, the volume of a sphere, in terms of the area. Okay, I know that volume is going to equal 4/3 pi r cubed. Okay, and I know that my surface area is going to be 4 pi r squared. Okay, now I could, for example, I could solve for r here, and that would get it in terms of A, sorry, and then do a substitution here. But that's making this out to be a little bit more difficult than it needs to be. What I'm going to do here is I'm going to use r as the link between those two. Okay, because they are both in terms of r here. So what I'm going to do is I'm going to take my derivative implicitly, once again, with respect to time, because time is the independent variable. So dV by dt is going to equal 4, okay, the 3's will cancel, pi r squared dr by dt, and I just love the fact that that happens here. Now, before you think, well, there it is, there's the connection. No, it's not. Because remember, this is dr by dt, and what I want is dA by dt. I mean, granted, I can plug the A into that, but that's not going to give me the relationship that I want. I want dA by dt. Okay, now I can manipulate this to figure out what dr by dt is, though. That's the one unknown that I've got. I know that this is going to be 2, 4 pi, and then this is going to be 12 squared dr by dt. And when I divide, okay, I'm going to bring this part down here. Now 12 squared is 144. Okay, and when I divide that 4 through here, I'm going to be left with another 2. Well, actually, I'll do it like this. We'll do it like this. This will be 4 pi times 144. We'll do it in steps like this. It'll be a little bit easier to follow. And then dr by dt, when I cancel that, this is going to be 1 over 288 pi. Equals dr by dt. Okay, so that's the rate at which the radius is changing. At the moment, the radius is 12 centimeters in this particular little bubble. Good. Now let's take a look at area. Well, the surface area, if I take the derivative of that, dA by dt, bring that down, that's going to be 8 pi r dr by dt. Okay, I'm looking for dA by dt. I know that my r is going to be 12, so this is going to be 8 pi times 12, and dr by dt is going to be 1 over 288 pi. Well, it's kind of convenient the way that worked here. Now, my pi's are going to cancel. That's good. And actually, I'm going to back this up a step because I know that this is 8 times 12, and I know that my 288 is going to be 2 times 12 times 12. So I'm going to factor things up a little bit just to make that easier for me to work with. So one of the factors of 12 is going to disappear. 12 has got a 4 and a 3 in it, and 2 times that 4 is going to be 8. So that's going to cancel and leave me just with a 3. So I'm actually going to be left with just a 1/3 when all is said and done. Okay? 1/3. Now, bear in mind that my dA by dt is in terms of r, which is in centimeters, and dr by dt, which is in centimeters per second. So this is going to be 1/3 of a centimeter squared per second. That's the rate at which the area is changing at the moment the radius is 12 centimeters. Here's another one. A car travels north at 40 kilometers per hour. Okay, travels north while, and in this particular case here, I think you almost need to read the whole thing to get a sense of the scenario here. While a second car, 80 kilometers north of the first car, travels east at 30 kilometers an hour. Okay, so what do we know? Well, to start off with, let's take a quick look at the compass here. A car travels north at 40 kilometers an hour. So here we go. And let's call this A, the distance that this guy is going here. So dA by dt is going to equal 40. Now, and at 40 kilometers per hour, I just ran out of, I probably should have thought that through a little bit more. While a second car, 80 kilometers north of the first car, okay, so this is going to be up here at 80, is traveling east. Okay, we'll call that B. And we know that dB by dt is going to equal 30 kilometers per hour. Now there's two different ways I could have set up the signs here, and I probably should have made this kilometers per hour. But there's two different ways I could have set up the signs here, but north and east are both naturally positive when you look at them compared to the coordinate plane. So it's easy to leave dA by dt as positive and dB by dt as positive. Okay? It travels east at 30 kilometers an hour. Now, how fast is the distance between the cars changing after 1 hour? So we're looking for this distance right here. We'll call that C. So I am looking for dC by dt. Don't know what that is. Now, in the first scenario here, the other bit of information I know is that time is equal to 1 hour. B is how fast is the distance between the cars changing after 2 hours. So B, 2 hours. And then C, at what time do they stop approaching each other and start moving away from each other? Okay, well that's an interesting question. So at what time do they stop approaching each other and start moving away from each other? So I'm going to have to think about that. We're going to have to take a quick look at what's going on here with A and B. Now, I do know what's going on here, but we might want to just see what's going on here and then see how that leads naturally to what's going to happen with C here. Okay, so we'll get right back to that in a second here. Now, notice, if we take another look at this triangle here, I'm going to draw this a little bit bigger to kind of emphasize one of the qualities here that we need to work on. It should be clear that we're looking at a Pythagorean theorem problem, but it might not be obvious how the information that we've got creates the actual triangle that we need. So let's take a look at this again. So here's the scenario. You've got this point right up here. This is 80 kilometers north, okay? And you've got this car right here, and it's going a distance A. So it travels distance A, and it's going dA by dt. That's how fast that particular distance is changing. This over here is going to be B. Okay, we know that dB by dt is equal to 30, and we know that this is going to equal 40. So then we're going to connect these two, and here's our C. Now, here's the thing. I would love this to be a squared plus b squared equals c squared, except that that distance there is not a. That's a, not that. Okay, the distance the car travels, okay, this car is coming up this way, it's moving up this way, okay. This, if you want to think of it like this car is kind of within the triangle, this one isn't. It's just below it. It's kind of pushing this part of it's pushing this point of the triangle forward. This one's pushing this one part of the triangle ahead of it. A, that distance is not part of that triangle. I'm still going to use the Pythagorean theorem. It's just that I need to use this distance right here. Well, this distance is going to be 80 kilometers minus whatever A is. So my Pythagorean theorem here, when I put that all together, is going to be 80 minus A squared plus B squared is equal to C squared. That's going to be the expression we're going to work with. And I hope that makes sense. Okay? I really hope that makes sense based on the diagram that we're given. Now let's go back up here, and we'll write that out here. So we're looking at 80 minus A squared plus B squared equals C squared. Okay. Now, we are going to take the derivative because I'm interested in the rates of change of these variables, not in the variables the way they sit right here. So I'm going to take the derivative. I'm going to take it with respect to time. That's the independent variable. I'm going to have to do this implicitly, okay, which involves using the chain rule, okay, that idea, and that's very specifically going to happen right here. So this will become 2, 80 minus a, okay, to the 1. It's going to be multiplied by negative 1 dA by dt. So I took the derivative of what was outside, bring down the 2, 80 minus a to the 1, took the derivative of that negative a, got that negative 1, and then the derivative of a, because it's some function with respect to t. Now the rest of this is going to be a little bit more straightforward. This will be 2b dB by dt is going to equal 2c dC by dt, because these are all changing in time. Okay, I am looking for dC by dt. dC by dt. So I'm going to divide everything through here by this 2c. Now, all of the 2's will cancel, and I'm going to be left with, okay, negative 80 minus a dA by dt plus b dB by dt. This will all be over c. Okay. Well, now I've got everything I need. I gotta fill it in. So let's take a look at what happens in scenario A. 1 hour later. Okay, let's take a look at this scenario here. After 1 hour. Okay. So let's do this here. So it's just part A here. After 1 hour, this distance here is going to be 40. Okay? Which means this distance here is going to be 40. So in that triangle, it's going to look like this. This distance here will be 40, so will this. This other car here will have traveled 30. And I know that C along here, because I recognize the pattern. This is my 3, 4, 5 triangle. So this is 30, 40. This is going to be my 50 kilometers. Okay, so here's where we start. This is where that car is an hour in. It's exactly halfway in between. And so that's the relationship between those variables here. So now I can come up here and I can start plugging stuff in. So this is going to be negative 80 minus 40. dA by dt is 40 plus b is going to be 30. dB by dt is 30 all over 50 equals dC by dt. Okay, so now what we've got here is 80 minus 40 is going to be 40 times 40 is going to be, that's going to be negative because the negative up front here, 1600 plus 900 all over 50 equals dC by dt. So I'm just going to do this over here in a calculator because once again, I don't want to start throwing down numbers that are incorrect and then feel like a bit of a goof. And so this is going to be negative 14 is my final answer here. And negative 14 kilometers per hour is dC by dt. Excellent. B. What happens in the second scenario here? Now, and by the way, negative, because what that means is, as this car is going forward, it's causing this distance to get smaller. dC by dt is getting smaller. Okay? Now, let's go to B. This is 2 hours later. Let's talk about this little scenario down here. 2 hours later means that what's happened here is this car has now gone up 80. It's going 40 kilometers an hour for 2 hours. That would be 80. So it's actually right up here at the top, right where this car is going over this way. So this distance here is 80. This distance here is 60. Now, bear in mind, here's where that first car is. Here's where that second car is. Now, what's interesting about this scenario here is that you don't get that triangle anymore here. It's just this kind of straight line between them, which means, well, A is equal to 80, B is equal to 60, but C is also equals to 60 because C is the distance between them. So 60 is the distance this car has traveled, but because of where that original car is now, that's also the distance between those two cars. So I go back up to my expression for dC by dt, and this is going to be negative 80 minus 80 multiplied by 40, how fast that's going, plus 30, B should have been 60. I'll just do this in a different order here. So this is my dB by dt. This is going to be multiplied by 60 all over, and then the distance between them is going to be 60. dC by dt. Well, 80 minus 80 is 0, so this term here actually disappears. So I'm left with 30 times 60 over 60. The 60s cancel, and I'm really just left with positive 30. dC by dt. Okay, whoops, and I should have written that as 30 kilometers per hour, which actually makes perfect sense. Because think about this. This car right here, when it's right here, its motion is straight ahead. But they are directly perpendicular to each other, so it's only this vehicle's motion that's changing the distance between them at that instant in time. And this one is traveling 30 kilometers an hour. That makes perfect sense. Now let's take a look at C. Okay? Because notice what happened here. In question A, an hour in, the distance between those is getting smaller. But here, 2 hours in, it's positive, it's getting larger. So somewhere in between the 1 hour mark and the 2 hour mark, the rate of change of C went from getting smaller to getting larger. It went from a negative value to a positive value. Now I want you to think about that. If you've got a variable here that's transitioning from a negative value to a positive value, at some point in time it must hit 0. That's the boundary between a negative and a positive. That's like saying if somebody is traveling, let's say from Canada to the US, they start in Canada, they end in the US, at some point in time they must travel over the border. That's exactly what we're saying here. So the question here is, when does that happen? When do they stop approaching each other and start moving away from each other? That is going to be where that dC by dt is equal to 0. Okay? And so now that is going to be where we've got, we don't know what the values are here, so it's going to be negative 80 minus A times 40 plus, what did we have here, 30 multiplied by B all over C. Okay, so remember dA by dt is 40, dB by dt is going to be 30. So we got to figure out when this occurs. And when I multiply through here, C multiplied by 0 there, well, that's just going to be 0. So that's going to be negative 80 minus A times 40 plus 30 times B. And when I multiply that through, okay, I'm going to get, that's going to be negative 320 plus 40A plus 30B. So 320 is going to equal 40A plus 30B. Okay, now you'll notice at this point right here that I've got one equation and two unknowns in it. Okay, I don't know what A should be. I don't know what B should be. Now that gives me a little bit of a problem here. Because how do you solve that? Well, you really can't. So what that suggests to me is that there was something a little bit wrong with our setup here. And actually the issue here is just a note here. In this particular case here, A and B both deal with distances that these cars have traveled, right? But remember, the independent variable is time. And in fact, this particular question is asking, at what time do they stop approaching each other and start moving away from each other? The first two questions are both talking about distance, how that one variable changes, how that one variable changes. Here, this is about when this change is occurring. So what we need to do here actually is set this scenario up in terms of time. So we're going to go back to our scenario here. Here's car A, here's car B, okay? This time, what we're going to do is we're going to come up with C, well actually A, B, and C here as functions of time. And so this right here, this distance that's getting traveled right here is going to be, okay, this is going to be 40 times time. That's how far, okay, that particular first car has traveled. This is going to be our A here. our B, the distance that they've traveled here, is going to be 30 times time. Okay? This distance right here, okay, this is going to be 80 minus 40 times time. So now notice I haven't actually done anything here. Okay? I mean, we knew how fast that car was going, so we know that distance is speed times time. Same thing up here. So all I'm doing is rewriting this, but I'm making sure that the independent variable here is now time. Now I'm still looking for when the dc by dt goes to 0. But now my setup is a little bit different. A little bit different. It's going to look different, but that subtle little change is going to make it easier for me to work with. Okay, so we're still using the Pythagorean theorem here. Okay, so now the distance here, though, because it's in terms of time, is going to look like 80 minus 40t squared plus, in this case, just 30t squared, and this is going to equal, this is going to equal c. Well, I wanted to put dc by dt already, so just c. Because the next thing I'm going to do is take the derivative. Now, in most of the questions that we do with related rates, time is implicit in the problems here, but now it's actually explicit. So when I take the derivative, I'm not going to worry about some of those other little issues that we need to concern ourselves with. I'm taking the derivative with respect to time. So this will become 2, 80 minus 40t multiplied by negative 40, and I don't need to worry about the derivative beyond that. Here, this will be plus 2, 30t multiplied by 30. Again, we're taking the derivative of using the chain rule, so bring down the 2, okay, multiplied by what's inside, and then the derivative of what's inside. Now, on the right-hand side, because c is some sort of function with respect to time, sorry, this was c squared up here, I should say, this is going to be 2c dc by dt. So I do have to take the derivative implicitly over there. But, just like we outlined before, I know that dc by dt is going to be equal to 0, so this will be 2c multiplied by 0. Now over here, when I multiply this all out here, when I distribute that negative, what is that? That's going to be actually negative 80 there, times 80, I'll get 6,400. When I multiply all those together, that is going to be, that'll be negative 6,400 because of that negative right there. And this will be positive 3,200t. And then over here, this will be, well, okay, 2 times 30 is going to be 60 times, that's going to be 1,800t. So this is actually fairly easy to work with. This is going to end up being 5,000t. I'll bring that negative 6,400 over. And so t, when I simplify that, that's going to end up being, what is 64 over 50. That's going to end up being, well, let's simplify this. So 64 divided by 50, I'll just see what that looks like. That's going to end up being, I was assuming that would go a little further, but 32 over 50, which is maybe not as, over 50. I completely wrote that down. I completely wrote that down wrong. 32 over 25, which is the same as 1.28. So at the 1.28 hour mark, the cars stop approaching each other and they're going to start to move away from each other beyond that point right there. Okay, now this question here's got an interesting little twist to it. So the length of a rectangle increases at a rate of 4 centimeters per second. Okay, let's take a look here. What do we know? Well, here's our rectangle. Here's our length, here's our width. I know that the length is increasing at a rate of 4 centimeters per second. Okay, so dl by dt is going to be 4 centimeters per second. Positive 4 because it's increasing. The width changes in such a way that the area is a constant 100 centimeters squared. Okay, well that's interesting. So I know that area is going to be 100. Now that's going to be length times width, and I know that's going to stay as a constant here. So at what rate is the perimeter of the rectangle changing when the side length is 10 centimeters? So okay. So I'm looking for the rate of change of perimeter, okay, at the moment that the side length is 10 centimeters. Okay, so at the side length is 10 centimeters. Now, let's face it here. Because the product of the length and the width is 100 always, I know right away that that means that the width is also 10. So this is essentially asking at what rate is the perimeter changing, essentially when this is a square. Okay? Okay. That's interesting. Now, let's just move forward here. I'm looking for dp by dt. So what is the perimeter going to be? Okay, that is ultimately what I'm looking for, so I need to have some sort of expression for perimeter that I can take the derivative of. Well, the perimeter is going to be 2 lengths plus 2 widths. Okay. Now, there are a couple of different ways that I can do this question. Okay? Now, to start off with, what I might do with this is take a look and say, okay, well, I don't really like the idea of having 2 variables in there. So maybe what I got to do is I'm going to do a substitution here. So perhaps what I'll do here is, because I know how dl by dt, or what dl by dt is, I should say, maybe I'm going to get rid of the w up here. Okay? And so I know, based on this expression right here, okay, I'll come down, I know that w is going to equal 100 divided by L. So now I've got an expression for w. And I can come back up and I can make this substitution. So perimeter is going to equal 2L plus 2, 100 over L. And so my perimeter is 2L plus 200 over L. And now I can take the derivative of this. So that's going to be dp by dt will equal 2 dl by dt. Now it's a little bit different when the L is in the denominator. Okay, remember that's going to be like L to the negative 1, so that's going to be minus, I'll bring down the negative 1, minus 200, L to the negative 2, so over L squared, dl by dt. Now that might look a little bit complicated, but at the same time, I know everything here. So now I can just substitute stuff in. So that's going to be 2 multiplied by 4 minus 200 over 10 squared, and then again dl by dt is going to be 4. Okay, so, well, 2 times 4, that's just 8. Well, 10 squared is going to be 100. Okay, so 200 divided by 100 is just going to be 2 multiplied by 4, and I hope you see right away, well, look at that, it's actually just 0. So what's happening here is at that moment, the perimeter has stopped changing. This is 0 centimeters per second. And that actually does make sense because the square, okay, when we start talking about quadrilaterals here, the square is a really efficient shape, okay, in terms of the relationship between perimeter and area. Okay, so let's say our length was increasing. So for a while there, what was happening there? The perimeter was getting larger. Now the perimeter is going to start to get smaller after that. Okay. Anyway, interesting problem here. But there's another way that we could have done this. I think I said that wrong actually just a moment ago. But anyway, doesn't matter. At that particular moment here, it's not changing. Another way that we could have done this, 2L plus 2W, was to simply jump in and take the derivative here. So dp by dt is going to equal 2 dl by dt plus 2 dw by dt. Now, the problem here is I know dl by dt, I do not know dw by dt. But what I can do here is go to that relationship 100 is equal to Lw, and I can use this to figure out what that dw by dt is. And I can do that by simply taking the derivative of this. Now I could get w by itself first, or, and I prefer to do it this way right now because I want you to see that you can do this, I can simply use the product rule. So the derivative of 100 is 0, and now I take the derivative of each of these variables at a time here, so it would be w times dl by dt plus L times dw by dt. Now, this is the part that I'm looking for. I'm looking for dw by dt. I know at this particular instant that I'm interested in that w is going to be 10. I know that dl by dt is going to be 4. I know that L is going to be 10. So what I'm looking for is dw by dt. So this is going to be negative 40 when I bring it over, is equal to 10 dw by dt. And I'll divide and I'll get negative 4 is equal to dw by dt. Good, great. Now I got that value. So now I can come up here and plug in. So 2, and we know that dl by dt is 4. 2, and now we know that dw by dt is negative 4. And again, when I put that all together, I get 0. So we've got this transition happening, okay, between the perimeter getting larger, the perimeter getting smaller. This will be centimeters per second. Doesn't really matter how you approach it, you should be getting the same result. Okay, everybody. This next question here is going to require just a little bit of preamble. What is the radius of the sphere at the moment that the rates of increase of its radius and surface area are numerically equivalent? Okay, so what do we know here? What are they setting up here? Well, we're being told we're looking for the radius. This is the thing that we want to know, and what we're being told here is that its rate of increase of the radius is equal to the rate of increase of its surface area, numerically. Now, however, writing it like this is problematic, okay? And I just want to acknowledge the fact that there will be people out there that will take issue with this, and I get it. Their point is valid. A dr by dt really cannot be equal to a dA by dt, and the reason for that is because of the units. This is in centimeters per second, let's say, and this is going to be centimeters squared per second. They aren't the same, okay? And so maybe a question like this really shouldn't be asked. However, you're going to find that there will be lots of people out there that will still ask a question like this. And so you really do need to be prepared for it. But just understand that there is an issue here, that we are playing a little bit loose with this derivative here because of the change in units here. So what this is saying is I've got my area, okay, and this is a sphere. We're still talking about a sphere. So area equals 4 pi r squared. And I'm looking for radius when there's a numerical equivalency between dA by dt and dr by dt. So I got to take the derivative here. dA by dt is going to equal, bring down the 2, 8 pi r dr by dt. Now, we're looking for it at the instant here that these two are numerically the same, even though in terms of their units they're not the same. But what happens here is this is going to be, whatever this is, okay, let's say that, for example, let's just throw in some numbers here. Let's say that dr by dt is going to equal, well, let's say x centimeters per second. dA by dt is going to equal, and at the specific moment that we're interested in, this is going to be x centimeters squared per second. So this is really going to become x 8 pi r x. But this is in centimeters squared per second. This is in centimeters per second. And so when I divide them, I am actually going to be left with the proper unit, okay? Centimeters squared per second, centimeters per second. I'll divide that out, divide through by the 8 pi here. So 1 over 8 pi centimeters is going to equal my radius. So, yeah, it's kind of an awkward question because, yeah, we're really kind of playing with that a little bit. This is what we're doing. It still works, and there's still going to be a lot of people that are going to be really comfortable with it, others that aren't. So it kind of depends on your teacher whether you'd ever see a question like that. All right, everybody. This question right here is notoriously difficult to get your head wrapped around. Okay, watched a lot of students struggle with it. and it is actually kind of hard to even to explain if some people get the kind of the wrong impression as to what's going on here. So I'm going to try to really make this make sense to you here. It's not a bad question though. A 50-meter rope is tied to the back of a truck so that it is 2 meters above the ground. Okay, now I know that that's maybe a little awkward, but the number is there just to make it a little bit better here. So here's what we know. Okay, I'm going to try to draw this out. So here's the back end of a truck, enormous tire, just an enormous tire here, because our rope is tied down to that truck right there, and this is 2 meters above the ground. Now that's high. But anyway, that gives you an idea here. Now, we're told that the rope is passed over a pulley that's 20 meters above the ground. So here's our pulley, and this is going to be 20 meters. So our rope goes up over the pulley and comes down to a weight. Okay? Now, the truck is going to drive away at 10 meters per second. Okay, so our truck here is going to move forward at 10. And I'm going to finish this diagram in just a second here because we're not quite done putting stuff on here to make this make sense here. But the truck is going to drive away at 10 meters per second. And the question is, how fast is the weight moving upwards when it is 8 meters high? Now, okay, it is going to be very, very tempting to throw a variable on here and make this distance here, like let's say y, and ask for dy by dt. And that actually makes a whole lot of sense. It really, really does. However, what makes a little bit more sense, the problem with that is how you relate this distance right here to the truck. I think it's a very natural thing to want to do, to want to build a triangle here. Okay? Now, the problem is, when you're laying out this triangle, okay, in order for this to work, this distance actually stays constant in this triangle. Now, I realize that that's a little bit hard to kind of get your head wrapped around here, because you're looking at this thing, well, no, the weight is going to fly up. That's true, but my right angle triangle doesn't get drawn to the weight. Okay? If I want to get the truck moving, for example, I'm going to call this x right here, the distance that this is from basically the straight line down along the pulley. That's my x. And so dx by dt is going to be how fast the truck is moving. And we know that the truck moves away at 10 meters per second. That's quick. Now, this is going to fly up here. But actually, this distance right here in this diagram, this distance, now not the distance to the weight, don't worry about that, but the distance from here, from the pulley to here, this is actually going to be 18 meters, and that's going to stay constant. Well, then you might ask, well, then where on earth does this idea of the weight going up come from? That actually is going to come from a different variable altogether. Okay, in this triangle here, we've got y and we've got z. Now, in this diagram, in this triangle, and you really got to focus on the triangle here, in spite of the fact that the truck is going this way, this relationship right here, the distance between the pulley down to that horizontal line, okay, right there where the rope is tied on, that distance is never going to change, because I'm not measuring the distance to the weight. I'm only talking about this right here. How do I talk about the weight flying up? This is the brilliance of this particular question. Whoever came up with this question, it really is a good one. What I'm looking for here is actually dz by dt. That's what I don't know. Now, that's the distance of the rope. Okay, that's the rope here connecting the truck to the pulley here. Because as this increases, this is going to fly up. If you pull on, if z gets 1 meter longer, y is going to get, the distance, not y, I shouldn't have said that. Y won't change, but the distance from the pulley to the weight is going to get smaller by a meter. So in this diagram, any change in z is going to correspond to a change in the position of the weight. And so that's where we're going to get our relationship from here. Okay, so we've got x squared plus y squared is going to equal z squared. Now we're going to take the derivative. Actually, sorry, we won't even take the derivative. Right now I'm going to do a substitution here. Now, normally I wouldn't substitute in values, but y won't change. Y is a constant. So now we get 2x dx by dt, okay, is going to equal 2z dz by dt. So this is fantastic. I'm looking for dz by dt, so I'm going to divide. The 2's will cancel. I'm going to get x over z dx by dt is going to equal dz by dt. This is great. We've got a wonderful little expression for how fast that weight is flying up. Because remember, the rate at which the weight flies up is directly related to the rate at which z is getting larger there. Except now we got a bit of a sticky little situation here. What are these values? Well, what did the question say here? Well, it said, how fast is the weight moving upwards when it is 8 meters high? Okay, so a little bit more information here. So the weight is going to be up here at 8 meters. Now, just again, so that you get a sense of the situation here. And again, this is another reason why this tends to throw people off. Here's our truck. Here's our rope going up. Here's our weight. Now at 8 meters high, it's going to be up here. Because remember, this distance here to the ground is 2 meters. And that pulley is way up here at 20 meters. Now I know my scale isn't, my diagram isn't to scale here. But just to give you an idea of what's going on here, this right angle triangle is the one that we're really focusing on, but that weight isn't part of it. Because if you draw the line from the truck to that weight, you get this weird triangle kind of developing here. It only becomes a right angle triangle for a brief instant. So I'm not worried about that distance. In fact, I'm simply going to look at the triangle here. And again, the clever part is relating the way this line changes to the rate at which the weight will fly up, even though the y part of this triangle doesn't change. Oh, I hope that makes sense. Okay, so now, with that little bit of information here, if I know that that weight is 8 meters up, okay, 8 meters up. Now let's think about this. I know that this distance right here from the ground, okay, from the ground up to the pulley is 20 meters. So if this is 8 meters, that means I have got 12 meters here, which means how much have I got left over? Well, the answer is 38 meters. Now, if you're wondering, where on earth did I grab 38 from? That's because we were told right up front here that there's only 50 meters of rope. So if 12 feet dangle down from the pulley to the weight, that means 38 is left over to connect it to the truck here. So Z is equal to 38 here. So now, here we go. In this triangle, because now that I know Z, that's great. I still don't know X though. So I'm going to build my triangle here. I know that this is 38. I don't know what X is. Now in this triangle right here, this is going to seem a little bit weird. This distance here, okay, was always 18. That never changed because again, remember, I'm not using the weight as part of that triangle, the position of the weight, just using the value of y, and that stayed constant here. Now, this is just the Pythagorean theorem, so x squared plus 18 squared will equal 38 squared. I'm hoping that this works out nicely, but I'm doubting it. And it doesn't. That's okay. So x is going to equal the square root, okay, of 1,120. So now I'm just going to plug that all in. So x is the square root of 1,120 over z, which is equal to 38. dx by dt is 10. Here's my dz by dt, so I'm just going to evaluate that now. Multiply by 10, divide by 38. And we get, at that particular moment here, that weight is flying upwards at 8 meters per second. That's the rate at which the rope is getting larger here, which is going to correspond to the rate at which the weight is flying up? Really, really good question.